Okay, so exam 3 went much, much better than any of the other exams. In my opinion, you can see the kind of the general histogram for it. There's a substantial portion of students way up on that higher end of the spectrum. So the average came out at a 73. Standard deviation, for whatever that's worth, is up there. There's also an extra piece of information on all of your exams. So you should have the total score on that front sheet, and then you probably also see some number with a letter followed after it, A, B, or C. So what I went through and did is projected forwards, because pretty much the only thing left is the final. There'll be one more quiz, but since we're dropping low scores on the quiz, it's probably not going to affect your grade very much. Okay? So really it's only the final that's left. Your homework, as long as you do it, probably isn't going to change your score either. So really it's just coming down to the final having an effect on your overall score. So what I went through and did is propagate it out and said, okay, what would you need to get to progress forwards or to maintain the grade that I would currently assign? So if you see the letter grade on your exam, that A, B, or C, in most cases that's where you are right now. Okay, that is your letter grade in the class. The exception to that is those people on the lower end of the spectrum. I figured you probably don't want a lower grade. So what I went through and did is said, what do you need to get a C? Okay? So if you've got a C, you're definitely in kind of a dangerous area. Check and look to see what your score actually is. So the intent behind this is that you can now go through and guesstimate what grade you're going to get at the end of the semester, or how much work you're going to have to put in. So what I would do is take a look at your average across the first 3 exams and compare that to the number that's written on there. Okay? If your average and that number are close to the same, if you maintain the effort that you're doing, that's probably the letter grade you're going to get. Okay? If they're drastically different from each other, for instance, if your exam average is much lower than what that number is, you've got a lot of work to do to be able to get that grade. Okay? If you want to know, because there are some people that are on borderline grades, you'll notice that your average is much higher than what's written on the exam, and that's because you were on such a borderline between those 2 categories that you were currently assigned the lower grade. So if you want to know what you need to get the higher grade, you can send me an email and I'll go through and discuss with you what exam percentage you would need. Okay? Does that kind of make sense? So the idea is to give you a rough approximation of what you're doing in the class and what you need to do to pass the final or pass the class. Any questions about that? I know it's a little bit confusing, but okay. Next piece of caution when it comes to looking at these numbers, these are to guarantee you that grade. Okay? If you get lower than that, that does not necessarily mean that you won't get that higher grade. That just means you're now coming kind of at the whim of the numbers. And if the numbers work out in your favor, sure, you get the higher grade. Okay? This does not take into consideration dialogues, because dialogues are strictly extra credit. Okay? I will assign grades according to where I see fit, and then I will go back and look at anybody on the borderline and look back to their dialogues to see if they should shuttle higher as far as the grades go. Okay? So that will only happen after I assign grades. Questions about any of that? Okay. Like I said, I think you all did quite well. To give you a heads up, actually I think this is on the next slide. So I went through and did the 3/4 semester grades. So after all of this, where do you end up falling, or where does the class end up falling as far as grades go? The approximate cutoffs are starting to creep closer to that 90 line. Again, I usually put the cutoffs higher than where I would at the end of the semester to make sure that you work harder to clear that cutoff. Otherwise, if you think you've got an A in the class and then you don't work as hard and you drop, I don't feel as bad because I gave you a 1%, 2% buffer to begin with. Okay? So one more piece of advice to help you out with that is the summer 2012. So last summer's final exam average was a 68, to give you an idea on classically how other classes have performed. In comparison, so far this class is darn close, if not a few points above last summer. Okay? So the numbers should match. I would expect an average somewhere in that 68 range for this final. Okay? As far as the final composition goes, we will definitely talk about it more next week, pretty much after I've got it written. It will be 50% old exams, so I will go through and pick questions out of exams 1, 2, and 3, and they will be verbatim on the final exam. I will change the question, or not necessarily the question order, the multiple choice order, so you can't just memorize answers or the letters. But if you want to go through and memorize all the answers, that's fine with me. Feel free to go through and do that. That's a lot of questions to memorize. Okay. The next 25%, or roughly 25%, will cover new material. So we're going to finish the electrolysis or the electrochemistry chapter today, and then we're going to do nuclear chemistry, and we'll probably finish that. My guess would be Monday of next week. Tuesday of next week is going to be looking at kind of applications into organic chemistry and inorganic chemistry. So looking at some of the more real-world applications as opposed to just numbers and numbers and numbers. Okay. Wednesday, I've got kind of planned in the back of my head to be a review. Okay, so I'll go through and try and organize slides as I see fit and put them into an approximate review presentation. And you guys can feel free to ask as many questions as you see fit to go through and do it. Okay. I will probably try and structure that review to cover where I think there are weaknesses, which is going to be looking at the buffers and acid-base stuff, because I think you would all agree that it appears to be everybody's weakness. Questions about any of that? Really? That was the fastest post-exam discussion we've ever had. Okay. So, electrochemistry. I just left up the numbers. I didn't actually change them at all here. Chapter 18 on final, those two questions for sure. You will see things like those. And then there's a few corrosion questions as well that will pop up, because those didn't actually make it onto exam 3. Okay. If you go through and take a look at the homework, both Connect and Sapling are up right now. The first 2 to 4 questions cover chapter 18. The rest of them are chapter 19. Okay. So we'll finish up with some questions there and then just jump ahead. So, our corrosion. We went through and spent pretty much the bulk of chapter 18 looking at how we control the electron flow. So we put separate compartments, we made galvanic cells, all sorts of fun stuff like that. But if we go back to our initial problem with that, when we looked at putting a zinc piece of metal into a copper solution, it went on its own. It did that redox reaction without us controlling it. It just did what it needed to do. Okay, so it was a spontaneous reaction. One of the things that we want to consider, particularly when we get into corrosion, is what happens if we can't separate these two things. Okay, well, the reaction is going to occur on its own, and it's just going to continue to go through and do it. Okay? Where this becomes important is when we look at examples of what we use as materials. So one of our primary building materials is iron. And one of the most common places to see iron would be somewhere submersed in water. Why would we submerge it in water more than likely? Nope, doesn't have to do with that. It's even easier than that. How much of the planet is made up of water? 70–80% of it. All of our materials are at some point going to come in contact with water. There pretty much isn't anything we can do about it. Our planet is based in water. We're going to see that exposure. So if we take our iron solid, take a look at our bottom case, and we go ahead and expose that to either water or oxygen. Why is oxygen going to be an issue? We breathe oxygen, which means there's a lot of oxygen in our atmosphere. That's why we can survive. So under the presence of oxygen or even acid, and acid in this case, most of our environment is slightly acidic, we can get a reduction reaction, okay, or a redox reaction. And in this case, we add these two up, we get a positive cell potential. What does that mean? If we just take iron metal and leave it out, it's going to get exposed to both water, which means our acid source, and oxygen, which means our iron is going to turn from a solid into the ion. What's the physical state of all of our ions? Aqueous. Okay? Which means we're taking a solid and we're turning it into a solution. Why is that important to us? Well, if you're in a boat, the reason you're in a boat is there's a nice solid surface that keeps you out of the water. What happens when that solid surface dissolves in water? You sink. So it's not a good option for us. What else is an issue? What maintains most buildings? Could go through and say concrete, but something has to support that concrete. It's typically rebar made out of iron. What happens if the iron corrodes? The structural integrity of the building is no longer there, and our building collapses. Okay? So we need to come up with some ways to control this exposure and prevent this reaction from occurring. Oh my gosh, I went through and balanced it all. Okay? So how can we go through and do that? So let's take a look at our reaction. What happens to the iron solid in our reaction? Might be easier to look at the half reaction. What occurred to our iron solid? It lost electrons. It was oxidized. Okay? So if it was oxidized, what did it act as in the reaction? Fair enough. Reducing agent. If we looked at an electrochemical cell, it acted as the anode. Okay? Oh, we already talked about all that. Sorry. Thought we were here. Okay? So what we want to do is go through and prevent that process. How can we prevent that from occurring? There's one easy way. Okay, that's a harder way. How about we don't use iron? We can get rid of iron altogether. Now we don't have to worry about iron corroding. Okay? There's limitations to what metals we can use and their physical properties. Iron happens to be a good one, so we can't get rid of it. So what we want to do is protect that iron surface. So we could coat it in some material. That material needs to prevent what? Even easier than that. The only reason the electron transfer occurs is because something's there to accept those electrons. If we coat it in a paint, where now that iron is not exposed to water or oxygen, does the redox reaction occur? No, because it's never exposed to it. So at our most basic and simple level, what we want to do is encase all of our iron materials in some surface that prevents the exposure to oxygen and water. Okay, well, that could work, except when you take a nail and you hit it with a hammer, typically what happens to the surface? It tends to fracture and break. We see cuts in the iron or cuts in our paint surface, which means that cut is now exposing fresh iron to the oxygen. We've got a problem. Okay? Now our nail can still corrode from within that tiny little spot. Okay? And it is a little bit more complex of a problem than this. But that's effectively what we're trying to do with this. Okay? So what we want to do is come up with something else to prevent that exposure. So we could try and do paint. What we're going to do is do something a little bit more interesting. What we're going to do is put another material there. That material will react preferentially over iron. Okay? So if it reacts instead of iron, what happens to the iron? Nothing, which means it stays a solid, our boat's floating, and our building stays standing. Good. So one of the more common things to do is you'll see something known as galvanization, which I think is zinc. Not positive on that one. What we're doing is we're coating the iron with some other material. That other material will react instead of the iron. That's our hope or our plan. So in that case, what we're doing is we're putting in another material to act as what? What's going to happen to that other material? It's going to be oxidized or reduced? Oxidized. Which electrode acts or allows for oxidation? The anode. So what we're going to do is generate another anode. Okay? This other anode we want to react instead. What we're doing is sacrificing it. So one of the terms that we come up with this is a sacrificial anode. What we're going to do is put in a better anode, something that's more likely to be oxidized than iron, which means the iron doesn't get oxidized. So your common phrase there is a sacrificial anode. What can we do to figure this out? We want to look at the oxidation potential for this new anode needs to be greater than the oxidation potential for whatever we're protecting. Okay, why does the oxidation potential need to be greater? More positive. Okay? Typically, though, we don't report things as oxidation potentials. We report them as reduction potentials. So the other thing that we could look at is instead of looking at the oxidation potential, is look to a table or a reduction table. And what we want to see is that the reduction cell potential or our reduction potential for the sacrificial anode be less than the metal protected. Why less than? Because when we flip it, it'll become more positive. Okay? Kind of makes sense? So, as far as printing or preventing or limiting, we already talked about paint. The other option is that we can paint on another metal. That metal can act as our sacrificial anode. Okay, it looks like I was right. When it comes to galvanized iron, what we've done is painted the surface with zinc. So that way, even if we expose some iron by scratching the zinc a little bit, the zinc is still going to react preferentially over the iron. It doesn't matter that the iron is exposed, because the zinc's still going to react first. Okay? Kind of makes sense? And we can see that by looking at those cell potentials. Let's see, did I move on? Yeah, let's go ahead and look at this. So what other materials might work to limit the effects of iron corrosion? We already said zinc was a good one, so we can go ahead and star that. What else would work? Aluminum? Anything else on that list? Lithium. How did we do that? We just said the ones that are more negative reduction potentials should protect it better. Okay? How do we decide which one we should use? That gets into a more complex issue. We should be able to reason through that. Do you know anything about the reactivity of zinc, aluminum, or lithium? Any one of those three? Lithium metal, when dropped into water, tends to be very, very reactive. Remember everything in that first row, except for hydrogen? All of those, what are they, alkali metals, I think is what we call them. When we drop those into water, they tend to react very, very readily. Those metal ions or metal atoms don't want to have that extra electron. So they donate their electron to a hydrogen atom in water. We generate lithium hydride. Lithium hydride reacts very, very quickly as a base and removes yet another hydrogen, and we release hydrogen gas. What we're doing is an acid-base reaction. Acid-base reactions tend to be exothermic, so they generate heat. And at the same time, we've also generated hydrogen gas. Okay, what happens as we go further and further down that table? It becomes more and more reactive until eventually, if we threw cesium in water, what happens? No one's seen that demonstration, really? Okay, good. Your 151 lectures didn't give you enough. They should have shown you that video. When you throw cesium into water, what happens? You get a massive explosion. Why is it so massive? You're generating hydrogen gas and heat. As we move down that table, it's being more and more likely to give up the electron. Okay, more and more likely to be oxidized. Okay, so it's generating that hydrogen gas with more heat. Eventually we reach a point where that heat energy is enough to ignite the hydrogen. And we get a massive explosion. Okay? Sometimes you'll see videos of them throwing lithium blocks into water, which is usually a bad idea. Okay? What happens to the lithium block? First off, it sinks into water and then usually gets launched out of the lake. Why? One of the byproducts is hydrogen gas. As the brick falls in, it starts to form the hydrogen gas. We build up enough hydrogen gas underneath the brick that it turns into a rocket and launches itself out of the water. Okay? So while lithium would be a great sacrificial anode, one of our issues was reacting with water. If lithium reacts with water so violently, is that going to be a good thing to coat our iron with? Probably not. Okay? So we need to look for other things that would contribute to it being a bad substance. Between aluminum and zinc. Any ideas on that one? That one's much trickier. What can you tell me about aluminum versus zinc? Anything? You seen aluminum before? How easy does it scratch? Really easy. Okay? Which means in the process of hammering it in, we're probably going to scratch a lot of that aluminum off. Okay? So we're going to end up losing our painted coating. If we lose the coating, does it protect the nail anymore? No. Okay? So what we have to do when we're moving into material science, which this is kind of an application of, is it's not looking at just the chemistry, but also looking at some of the physical properties behind these. As far as an exam goes, I wouldn't throw lithium on there as something to protect because that's just an awful idea. But between aluminum and zinc, if we look only at corrosion, or electrochemically speaking, which one of those should be the better protector? The aluminum, because it has a better oxidation potential. Okay? When we look only at the electrochemistry, if we start to move outside of the electrochemistry into physical properties, that's when our opinions start to change. So every problem that you encounter in anything is going to have different levels that you need to be concerned about. Okay? Wow, I got quiet. Other things that can be interesting to consider when we look at these, just to get you an idea of more things, how it's complex. If we look at even aluminum or zinc, and we did that as a coating, okay, eventually all of the zinc, so zinc tends to be one of the best choices. Okay? If zinc reacts, so let's say we leave our nail there for an infinite amount of time, eventually what happens to the zinc? Fully reacts into the ion, which means it's gone, which would then mean the iron could now react, and we could go through that corrosion process. Okay? Just to give you an idea, and again, this is why it's a lot more complex than just looking at the electrochemistry. One of the other things that we can evaluate is what happens to that species when it reacts. When we generate zinc ion, it actually goes through a secondary reaction and reacts with oxygen to form zinc oxide. There's a special property of zinc oxide that's different than iron oxide, which is rust. Zinc oxide is not porous. It actually holds up better than the zinc metal itself, which means as the zinc actually oxidizes, it generates yet another protective coating around our iron nail. Okay? You're not responsible for knowing that. I'm just trying to let you know other things that can contribute to these. Okay? So there's differing levels of chemistry that you can get involved in to determine what's happening for each of these things. Okay? Questions about corrosion?
analyze metals and their
Yep.
reactivity with water, how come we're able to put sodium in water all the time?
Do we put sodium in water all the time?
Salt.
We put sodium ion. The ion is drastically different than the metal. The metal does not want to have that electron. What is sodium ion? It's sodium metal without the electron. Okay? So when people talk about, oh, this species is so dangerous, yeah, sodium is incredibly dangerous, and if anybody ate that, you'd probably be dead. Except you don't eat that. What do you eat? Sodium ion. Sodium ion is critical for our muscle function. Okay? So when people start talking about different reactivities of different species, you have to make sure that they know what they're referring to. Are they referring to the metal? Are they referring to the ion? Okay? Because every different species is going to have slightly different reactivities, even when we look at the ions. Okay? So one of the reasons why people are so scared of chemistry. Okay? You say, oh my gosh, sodium's going to kill me. No. Okay, sodium ion will kill you. You're never exposed to it. Okay, so you have to be aware of what people are talking about. Okay, make sense? As we look at a little soapbox discussion on chemistry. One of the last things that we ended with before we moved into exam 3 was the Nernst equation. There was one question looking at the Nernst equation, which was just a direct application on your exam. Okay? What is Q? It's our products over our reactants. So if we know the concentration of our products and we know the concentration of our reactants, that's going to cause our cell potential to change. In most of the cases that we looked at, we said standard cell conditions, which meant all of our concentrations were 1, products and reactants. The natural log of 1 is 0, which means this term drops out in most circumstances, or in a lot of circumstances, and we get our cell potential equaling the standard cell potential. But what happens if they aren't 1? We would have to go through and solve this equation as shown, plug in what we know about our products and reactants, and see what happens to our cell potential. Okay? The interesting applications in here are concentration cells, and for that matter, pH meters. Okay? Though I didn't put anything on pH meters. pH meters rely on a similar process, hydrogen ions coming across a cell membrane and reacting with a silver electrode. Okay? And we can convert that electric change, or that electric potential, into a concentration of hydrogen ions. So it's kind of neat when we look at the pH meters. As far as concentration cells go, so what we want to do is kind of go through some thought games first and get an idea of what can potentially happen in each case. Okay, so if we go back to our standard electrode, or our standard voltaic cell with our zinc and copper ion, we know our standard cell potential was 1.1. How do we know it was 1.1? A couple ways to do that. Number one, we've been working with zinc and copper ion as electrodes or voltaic cells now for a week. And in each of those cases, we calculated it out to be 1.1, which means our standard cell potential is going to be 1.1 because we trust what we've been talking about in lecture all week. Okay? The other way, go back to your lecture notes and calculate it. Use the standard, or our cell potentials, reduction potentials for our zinc to zinc ion and copper ion to copper metal. Okay? And you should still get that 1.1 volts. Okay? If we are at standard conditions, what is the potential that we see? What does it mean if we're at standard conditions? Don't tell me all at once. I might get confused. We know the concentrations of our reactants and our products are all equal to 1. All metal or all solids and liquids are pure, so they don't appear in our equation. And we can go through and we can say our cell potential equals RT. Sorry, let me get out of your way. Times the natural log of our product, what is our product in this case? zinc ion. What is our reactant? Copper ion. If we're at standard conditions, the concentration of those two species was 1. 1 divided by 1 is 1. Natural log of 1 is 0. So in case A, what is our cell potential for that reaction? 1.1 volts. It's exactly equal to our standard cell potential. Okay, which makes sense. We're at standard conditions. It should be equal. What happens if we now let that reaction go? Okay, say 10 seconds later, or 30 minutes, or 2 years. What happens to our concentrations? They should change. In theory, if we set this up right, they're going to change until they get to equilibrium. Okay? If we set this up to be a positive cell potential to begin with, we're looking at a spontaneous reaction. Q needs to be greater than K. So what happens as we run the reaction? What happens to the zinc concentration? Does it go up or down? Where is zinc? Product or reactant? Product. Zinc ion, sorry. Where is zinc ion? Product. If this was a spontaneous reaction, we are progressing towards what? Towards our products, or a copper solid. Okay? Which means as the reaction progresses, what happens to the concentration of zinc? Zinc ion, sorry. It increases. What does that do to our cell potential? If this concentration increases, what happens to our copper ion? Decreases. So this value starts to get bigger and bigger. The natural log of a big number becomes, did I do that right? Bigger, smaller. Natural log of a big number, what do you get? What was that? Who's got it? Who's got a calculator? So what are you saying? Bigger than 0. What do you get back there with a calculator? Do natural log of 10. Greater than 1. Okay. Do natural log of 0.0001. What is it? So as we go to a really small number, we start to see, or a number less than 1, we start to see the natural log become negative. If we're greater than 1, what happens? It's positive. How does that affect our result? If we start generating more products than reactants, this number is positive. What's the sign on Faraday's constant? Sign on N. R. T. Positive. What's the cell potential minus a positive number? Less. So as we let our voltaic cell run, do its own thing, what happens to our measured cell potential? It gets smaller and smaller and smaller until eventually what happens? We get to equilibrium. What happens at equilibrium? Our cell potential, if we don't have a spontaneous reaction either way, what happens to the cell potential? Becomes 0. Okay? So as we run a reaction, eventually, over time, our reaction is going to progress to the point where we do not have a measurable cell potential. Okay? Does that make sense? If we take a battery, which is a portable voltaic cell, and we plug that into our equipment, yay, we get power. What happens eventually? It dies. Why does it die? Because we've reached equilibrium within the battery. The forward and the reverse reactions have balanced each other out, and we now have 0 cell potential, which means no more electric flow, which means no more power to our device. Okay? So that's a bad situation, so let's invert it. Can we make the cell potential bigger than our standard conditions? Can E ever be greater than the standard cell conditions? We already looked at one option. What happened when we were Q less than 1?
Negative.
We got a negative number. So if this is now negative, these are all positive, what happens when we do a negative times a negative? Becomes a positive. What happens to our measured cell potential? It goes up. So we can set up a system such that we get more power out of it, or we can prolong the power usage by tweaking the concentrations of our reactants and products. Okay? And that's the huge application of the Nernst equation, is trying to evaluate so that we can now tweak our conditions to maximize our longevity of our battery. Okay? So we can generate a cell potential that's greater than that. This is a fun question as far as I'm concerned. Okay? So if you go back to exam 3, I think summer 11, because I don't think it showed up on the summer 12, there was a question about permanganate and changing different variables, pH, concentrations. That whole question is based solely around this equation, looking at the Nernst equation and applying what those changes do to the concentrations of products and reactants. How does that translate back to your cell potential? Okay? Which involves zero calculations, which is one of the reasons why I like it. Okay? So you will see some application of this on your next exam. Okay? As we already discussed, if we let our reaction run forever, eventually we reach equilibrium. So our product concentration goes up, our reactant concentration goes down until Q becomes K. And what we end up finding out is that our Gibbs free energy equals 0 because we're at equilibrium. We can do some substitutions. Whoops. And we end up finding out that our cell potential will also equal 0. Okay? Questions about that? So one of the things that's kind of neat, when we looked at chapter 14, 15, and 16, a little bit of 17, we were driving for equilibrium. That was our goal. We wanted to be at equilibrium because then we could do all these fun calculations. When we look at electrochemistry, how important is it to get to equilibrium? Not. And in fact, we don't want to be at equilibrium, because if we're at equilibrium, we've lost all potential application for electrochemistry. Okay? So it's a slightly different spin on looking at the similar materials. Questions about that? Okay, so let's push it a little bit more. Let's set up a voltaic cell, and for the cathode and the anode, we're going to use nickel metal, so the exact same species. For the solutions that those electrodes are going to be in, we're going to use nickel nitrate, so the exact same solutions. Assuming the rest of the cell is set up properly, so don't give me this, there's no salt bridge stuff. Okay? What happens, or what voltage can be measured? Okay, should we ever be able to measure a voltage? Seems a little bit tricky. One thing we could go through and do first is calculate a cell potential. Please say that's what I did here. So we could set up our reactions. At the anode, we're looking at what type of a reaction? Oxidation. So we'll take nickel solid, take it to nickel ion to generate 2 electrons. Oxidation. We can look up our reduction potential. It's negative 0.28. If we turn that into an oxidation potential, it becomes if it's an oxidation potential, it becomes thank you, positive 0.28. At the cathode, what happens at the cathode? Reduction, or a gain of electrons. So let's take nickel ion plus 2 electrons to make nickel solid. That's a reduction, so we look up our reduction potential, we get negative 0.28, go figure. What's our standard cell potential for this reaction? 0. So one of our potential answers would be no, we can't measure a voltage. But what does that assume? Not even at equilibrium. That assumes we are at standard conditions. What happens if we're not at standard conditions? Okay, so at standard conditions, Q becomes 1 because our product concentration, nickel ion at our anode, divided by our reactant concentration, nickel ion at our cathode, both those concentrations are equal to 1. 1 over 1 is 1. Natural log of 1 is 0. So what do we get? Our cell potential for that reaction equals our standard cell potential, 0. We'd say, oh no, there's no way we could get a cell potential there. Does the question say anything about concentrations? No. Okay. So it's not saying that the concentrations are all 1. That would be our assumption put into it. So what happens if we switch that up? Okay, let's say it's not 1. Let's go through and change our conditions. Okay, so we're going to have two possible conditions. We're going to have our values where the natural log of Q could be greater than 1 or less than 1. What happens in each of those circumstances? If the natural log of Q is greater than 1, a positive number times all of these positive numbers, 0 for our cell potential minus a positive number gives us a negative number, which says no spontaneous reaction. We could assume we don't see a voltage, which is kind of questionable. We'll come back to that in a second. Okay? So we'd say, no, we don't get a cell potential there. But what happens if our natural log of Q is less than 1? Now if we go through and do the substitution, our cell potential will be roughly equivalent to our standard cell potential of 0 minus some negative number, which means positive cell potential. Kind of interesting. What does that mean? With two species, both the anode and the cathode, having the exact same materials in it, we can still generate a cell potential, even though our standard cell potential is 0. Okay? It's kind of a bizarre concept. How does that end up working? Okay, well, actually, one of the more interesting things here is that we're looking at what's known as a concentration cell. We've built a gradient where the concentration wants to balance out. Everything wants to reach equilibrium. We're going to try and increase and decrease, respectively, the concentrations of our ions in each compartment until they equal each other. Okay, where have you seen that before? Anybody in biology? Process of osmosis. Okay. Everything tries to standardize and reach the equal concentrations. So what we're doing is forcing that natural process to occur. But at the same time, if we have the ions flow from one electrode to the other, what happens to the charge from our initial state? Charge changes. We can't have our charge change, so what has to happen? Electrons must flow through the wire to balance out that overall charge shift with our ions. Okay, so what we end up generating is an electric current from our ion flow. Okay, is that even remotely possible? Well, how did we get our electric current to begin with? When we look back at the very beginning, we said we were monitoring the electric current. What if we didn't have the salt bridge? Could we get an electric current? No. We needed the salt bridge for that reaction to occur. Okay? In this case, what we're looking at is now pretty much the opposite. To get the ions to flow from one place to another, we also have to have electric current set up. So what we would have to do is just put up a wire, and we can now see the ions flow as well. Or sorry, our electrons flow as well. These two processes are intricately linked. They're one of the reasons why we have any energy whatsoever. Anybody heard of ATP? How do we generate ATP? Well, that's really pulling at straws, probably. No biochemists. From ATP synthase. Okay? Powerhouse of all life as we know it. Okay? What happens to get that enzyme to work appropriately? This may still be pushing at straws. Hydrogen ion needs to flow from one side of the cell membrane to another. Why would the hydrogen ion flow across the membrane? Because there is a concentration gradient. That concentration gradient allows for us to store chemical energy. What are we doing here? We're taking advantage of a concentration gradient to generate electrical power. We're doing the exact same thing that our bodies are doing right now to keep us alive. Okay? So it's kind of a long-distance application that you may not necessarily see. It does come back to this material. So it's actually kind of neat. If you hadn't thought of that before, I hadn't thought of it either. I just thought of it this morning. Kind of weird. It's like, oh, that's kind of neat. So what we can do is look at the relationship between those equilibrium constants and try and come up with an expression to tie this all together. Where this becomes difficult is when we go through and look, or more difficult if you want, if we take a look at Q, it's product over reactant. What's our product ion? Tell me what the product ion is. Nickel ion, what's our reactant ion? Nickel ion. Are those two nickel ions the same thing? No. If they were the same thing, it wouldn't work out. How are they different? There's a reason it's color-coded. One nickel ion is blue. One nickel ion is red. What is that color coding actually implying? The location of the ion. The red nickel ion is in the cathode. The blue nickel ion is in the anode, which means they're distinctly different species. They're in different locations, different compartments. So when we go through to try and plug in numbers, we have to be very careful that what we're putting in as our product is the ion concentration of the species located in the anode. When we go through to determine the reactant concentration, it's the ion species located in the cathode. Okay? In most Nernst applications, and what you saw on your previous exam, those two species were very clearly different. I think the exam was, actually I don't remember what it was. Okay? We looked at, say, tin and gold. Okay? You can look at the name, the symbol itself, to be able to tell the difference. Here what we have to do is look at its location, because we're looking at that concentration gradient between two different compartments. Okay? So it's a lot more of a tricky application. So what we're hoping to get is that our product concentration is less than our reactants. Why? Because that gives us a Q that is less than 1. If our Q is less than 1, that means our natural log of Q is, less than 0. And we get a negative number, which then allows us to go through and solve for our expression. Okay? Or get a positive value. So where does this become important? How can we remember this? Q in this case is the nickel concentration at our anode divided by the nickel concentration at our cathode. That's what we need to use for our Q value to generate a positive cell potential. The concentration at the cathode needs to be greater than the concentration at the anode. Okay? So we would have to go through and make sure that if we were given two concentrations, that we put them in the appropriate spot in the equation. Because if you didn't put them in the appropriate spot, what happens to your cell potential? You get a negative value, not the positive value. Okay? So you have to be very careful with those applications and sliding them into the correct spots. Okay? Another way that we can look at this is instead of looking at nickel ions, let's just do it generically, ions. To get a positive cell potential, the ion at the anode needs to be less than the ion at the cathode. Okay? Questions about that? I know that one's a bit far out there. Or some people are shaking their head, meaning it's not that far out there. Okay. Batteries, yay! That's about all I got to say for batteries. Yay! Okay. There aren't a lot of questions I can ask about batteries, pretty much because it's strict memorization. Okay. As you've already seen, I'm not a big fan of strict memorization, which is why I give you all the equations to work with. So you're not going to see any real exam questions come back from batteries. Okay. The textbook lists off a whole bunch. I listed a whole bunch here, so you get an idea of what's going into each. They do a discussion of rechargeable versus non-rechargeable. The rechargeable ones just mean that we can force electrons in to force the reverse reaction. Okay? The non-rechargeable ones have pushed to a physical state that we can't change, or we can't change easily, which means our reaction is dead. There's nothing we can do to fix it. Those are typically your alkaline. They're based on hydroxide. So I think in the process of that, we end up converting hydroxide over to water. To get that reverse reaction, we can't do that. Okay? We just don't have the physical capabilities to reverse that reaction easily. So that battery ends up dying, something along those lines. Okay? Our rechargeable ones, we're looking at different ions where we can reverse the voltage on them and cause the reverse reaction to occur. Once the reverse reaction has occurred enough, we can then pull our battery out, and now it's going to spontaneously go the other direction. Okay? So we can build up enough charge in there that it actually maintains. Okay? Eventually, we can't do it anymore, and that's because other reactions occur and end up changing the physical states of the species within each battery. We can't use it anymore because it's in a different state. Okay? Be it physical state or oxidation state. Okay? One of the last fun things to take a look at would be electrolysis. Anybody see what's going on with that title? What is it? Electrolysis is the reverse of a voltaic cell. Pretty much the exact same system. All we're doing is spinning the voltage on it. So instead of letting the electrons naturally flow, what we are going to do is force electrons into our reaction. Okay? Why would we go through and do that? Well, what we can do is force gold ion out of solution. Okay? A couple interesting applications there. I think I actually read this in your textbook. During World War II, one of the Nobel Prize winners decided to dissolve their gold metals, their Nobel Prize metals, because they're all made out of gold, into ions. Why? Because a solution of gold ions looks an awful lot like water, completely worthless. Why would you do that? Because the Nazis were coming in and they figured if they saw the gold metals, they would steal the metals and they'd lose their prize. So they dissolved it into ions, put it up on the shelf. What happened? The Nazis come in, oh, there's just water, we don't care about it, we leave. What happened after the war? They came back, took their solution, reversed the reaction, and now they had all that gold crystallized back out. They didn't have to worry about the Nazis stealing it. Okay? What's that? I didn't hear what you said.
You must have read something about a periodic table.
About a periodic table? Just a few. Okay? So one of the things that we can do beyond saving gold from Nazis is you can make cheap, expensive-looking jewelry. Okay? Everybody wants pure gold things. So what can we do? Well, we can plate gold onto cheap things and then sell it for more money. Because, hey, look, I swear it's solid gold, I promise. You know, don't buy watches from the street for that reason. All they're doing is plating gold onto something else. Okay? So we can put materials into these baths of ions and force the reaction to occur the other direction and plate out expensive metals in very thin coats. Okay? We can paint iron surfaces. Remember when we looked at iron, we were trying to get zinc onto that surface? Well, if we want just a thin layer of just pure zinc, we need to come up with some way to get the zinc metal scraped onto the iron somehow. The way we can do that is through electrolysis. Okay? We can generate hydrogen gas. Hydrogen gas for almost all fuel cells ends up coming through a version of electrolysis. we hydrolyze water to generate that hydrogen gas. Extremely expensive process, by the way. And then we can also look at the production of oxygen, also through hydrolysis of water. We use that for our spaceships and submarines. So it's kind of a neat application there. And then we can also use it as a refinement process, which you guys in lab have already seen. How did we get pure copper out of our ore sample? We first converted it into the ion, and then we pumped electric current into it. What did that electric current do? Shift our ion over to the copper metal. Okay, so we can cause or use it for a refinement process. So it's a huge, huge industry as far as it goes. The next part about this is looking at quantitative electrolysis. So those of you in lab, again, have already seen this calculation, but we'll walk through a couple examples here, make it a little bit more interesting. That's a lie. Sorry. It's probably not that much more interesting. Important conversion factors. So really, when we're looking at an electrolysis problem, they're all conversion factors. There isn't anything more difficult about it other than just converting one number to the next. Okay, so it's a 151 level calculation. You don't have to worry about barn charts or ice charts or anything like that. You just go through and convert. Typically, our input energy is in the unit of amperes, which means we need a conversion factor to get from amperes into something else. 1 ampere is equal to a coulomb per second. Okay? One of the important aspects of this is not just putting electric current in, but also the time that we spend putting electric current in. Because if we only spend a few seconds, we're not going to put a lot of electron count into it, which means we're not going to get a lot of stuff out. So we're also going to incorporate time. Typically, we would work in seconds because an amp is a coulomb per second. Okay? So if you want to switch to different units, that's fine. I don't think you'll find anything already solved for you as far as different units. So what you'll have to do is convert whatever time you're given into units of seconds. In theory, you know how to do that, right? 60 seconds is a minute, 60 minutes is an hour, 26 hours in a day. Just checking, 24 hours in a day. The other big conversion factor is Faraday's constant. We can look at, that one's actually written out wrong. Faraday's constant, we can use coulombs per mole of electrons. If we bring in the joules, we have to bring in volts. What we really want is coulombs per mole. Why is that helpful? Well, our amps we can eventually convert into coulombs, but we need to be able to convert those coulombs into an amount of electrons. How do we do that? Faraday's constant. We now know how many electrons we've pumped into the reaction. The rest we need to be able to figure out by looking at balanced reaction equations. How many moles of electrons are needed to do a particular conversion? Okay? So let's go through and do one together. How many grams of aluminum will be produced in 1 hour by the electrolysis of molten aluminum chloride if the input electrical current is 10 amps? Okay? One of the first places to start, which is fairly standard for almost everything we've been doing, is to start with a balanced equation. So what we're going to do is take aluminum chloride and turn it into aluminum. How do we know that? It may sound like a simple answer. That's what the problem tells us. How many grams of aluminum are produced, which means aluminum is a product, from molten aluminum chloride, which means aluminum chloride is a reactant. So we can set those up on opposite sides of the equation. The chloride can be a bit confusing. When we go through and do this process, we're going to end up having both an anode and a cathode. Okay? Our chloride is going to be involved in the other reduction or oxidation reaction. Okay? So what we can do is, instead of doing aluminum chloride goes to aluminum, we can make it aluminum ion. Aluminum +3. Why is it a +3 charge? Because chlorides are all -1, and there's 3 of them. Okay? So we can simplify that. Oh, shucks, I thought I did the ion. Okay? We could go through and look at our oxidation states. Aluminum +3, which we just established. Going to aluminum metal, the oxidation state of aluminum metal is going to be 0 because it's in its elemental state. Okay, there's no charge written there. To get that balanced, we need 3 electrons. So we can put the 3 electrons on the other side of our equation. Yes? Okay. We don't have to worry about the chloride. I did happen to include it in this case, but since the chloride isn't being asked about, we don't have to evaluate it. Okay? So the next problem says we start with 10 amps and we do it for an hour. So what we're going to have to do is crunch out some conversions. We take 10 amps times an hour. Okay? We know amps. Oh, I didn't show that conversion. That's kind of mean. What's the extra conversion that's not shown there? One amp is equal to 1 coulomb per second. Okay? So our amp unit can cancel out. We then have coulombs per second, but we have time in hours. So to get our units to convert, what do we have to do to our hours? Our units to match. We have to convert our hours into seconds. 1 hour happens to be 60 minutes. 60 minutes happens to be 60 seconds. And we end up now with our magic number. We put in 3.6 times 10 to the 4th coulombs. Okay? We're trying to get this into aluminum metal. Okay? We don't have a unit yet that we can work with. Can we convert coulombs to something from our equation? Say through a magic Faraday's constant. Okay? Faraday went through and did our conversion for us, so we can now incorporate that conversion. Okay? We can convert our coulombs into moles of electrons. We now have moles of electrons. Can we convert moles of electrons into anything? Say through a balanced equation. We know that the moles of electrons are related to the moles of aluminum. Oh, wow. Come on now. 3 moles of electrons is equal to 1 mole of aluminum. So after putting in that current for an hour, I would expect to generate 0.124 moles of aluminum. Hooray, that answer's on your key, or on your possible answers. Is that the right answer? No, why not? Asked for grams. How do we convert moles to grams? The molar weight, or the molecular mass. And we now have the mass of aluminum produced. Okay? This is one of the more straightforward calculations as far as electrolysis goes. The other ones that you'll see on the homework would be looking for time, units of time. Okay? So go through and try and use the information that you've got and slowly convert your way through to each of those individual pieces to solve what you're looking for. Okay? If you track your units won't fail you. Okay? Questions about that? So I'm going to leave you guys to work on this one, so we'll spend the next 10 minutes doing this problem. This one's a lot more difficult. What is the concentration of copper-2 ions after a current of 2.3 amps is applied for 25 minutes to a 500 milliliter sample of 0.1 molar copper-2 sulfate? Definitely a tricky question.